Yeah. So yeah, thanks a lot for the invitation. So maybe two caveats before I start. So I'm not an expert in singularity theory or in real geometry. So this is a bit of a new area for me. So yeah, please correct me if you know more than me on this topic. And the other thing is that I apologize, but the paper is not on the archive yet, but it should be over the summer. All right, so I will start with a sort of elementary question. Well, let me just think. In fact, most of the talk will be about this invariant. I will explain how. I mean, it's a very nice and elementary invariant, but I think it's quite interesting, and there are lots of questions that one can ask about it. So let's start with some kind of elementary questions. So so I start with an analytic function, and let's say a non-negative analytic function on Rn. And I can associate to it two objects. So first of all, I can look at this M state scheme. So this is going to be the set of sort of Taylor expansion of curves in RD. So in other words, I choose a starting point, then I choose a tangent vector, then I choose the Taylor coefficients or the two, and so on. So these live. I mean, I just record all these Taylor coefficients. So these live in RB to the n plus 1, and I'm looking at those such that when I apply f to it, I get something which is 0 up to order. Yeah.
So the sequence terminates, right? That t to the.
Oh yes. So
okay.
So what are these objects? Well, they are real analytic sets, real analytic subsets of this thing, which deserves to be called the Jets scheme of RD. And they are a small, I mean, generalization to the real analytic case of the jet scheme in complex or in algebraic geometry. And I mean, as is well known in algebraic geometry, their geometry sort of records a lot of interesting information about the geometry of the singularities of F. And so that's a kind of, I mean, even though we're working in this analytic setting, this is really a kind of algebraic object. This is defined by some. I mean, it is somehow relatively algebraic over the zero set of F. And on the other hand, we can look at something really analytic, which are exponential integrals. So, and this will maybe depend on some sequence sets. So assuming these integral converge, I mean, I'm not going to worry about that for now. So those are generalized exponential integral or generalized Laplace integrals. And the question is, what do these two things have in common? And let's look at a simple example. So as a quadratic form. So first of all, yeah, what is J0 of Q? J0 of Q or J0 of F in general is always the zero locus of F. So this is just actually a point inside RV. Now, if you think about, I mean, that I will leave as an exercise that any tangent vector, I mean, because you have these squares, any tangent vector works here for the J1. So in particular, this is isomorphic to RD inside of R2D, and then I leave it as an exercise to check that GM is going to be RD to the m+1/2 inside of this of our RD m+1. So in particular, the codimension of GM so inside this ambient jet scheme of Rn, sorry, of Rd, divided by m+1 is d/2 of m odd, and d/2 times 1 plus 1/m+1, I think. Yeah. For any given. And basically, the one thing that I want to remember about this is this operation d/2. Now let's look at the integral, right? This is an application of the Gelfand integral. So if I look, in this case, I can even look at the integral over the whole of Rn. And by Fubini, this is just the d's power as a Rd. I want to keep my notation consistent. The n is this n, and the d is the dimension. So it's just the same thing with R. And so this is just 5d/2 times n to the -0. And okay, and the basic claim is that this is the same d/2, and this d/2, this common d/2 is what's going to be called the real log-canonical threshold. And I will abbreviate this by RNCT, which is simple, of Q. And so this is this. I mean, this is a very simple example, but this phenomenon will basically hold in a form that I will make precise for any real analytic function. Any question about the introduction? So then I'm going to spend most of the talk talking about this real log-canonical threshold. So again, I mean, let's be slightly more general, but I mean these invariants are basically local invariants of singularities. So the generality is really kind of artificial. So I take a real analytic manifold, and I take f, so a real analytic function on x, and to simplify my life, I'm going to assume that the vanishing locus of no, so yeah, I'm going to assume some kind of plainness of F. So you assume that there exists some compactification of x such that f extends to x large, just it's kind of finiteness condition. So this is true for polynomial. Well, maybe that's not exactly what I want to say, actually. Okay, yeah. So what's the definition of this quantity? Well, there are many equivalent definitions, and I'm going to present a few. But this RCT of f, which I will denote to simplify my notation by lambda of f. This is by definition the supremum of positive real numbers, such that f to the absolute value of f to the -s is locally integral. And here I'm not assuming that f is non-negative. And then similarly, if I have a point x in x, I can define the local quantity, local real log-canonical threshold, which is the same thing, but it's locally integrable. Here you put a locally integrable around at x. Small unit neighborhood of x. Let's do a simpler possible example, which is so in dimension 1, f. Sorry, so yeah, I will always have dimension of x equal to b. But so in dimension 1, so f of x is x to the n. So I mean, when is x to the minus ns locally integrable on R? Well, exactly when minus nx is greater than -1. So it's equivalent to s smaller than 1 over n. And so this implies that the lambda of x to the n is 1 over 4. So it's a really analytic definition. So I guess 2 remarks about this. I mean, the first one is that the intuition that you should have is that this measures how kind of degenerate the singularities of FR, and so this will be made precise in various sort of analytic ways later. So the smaller lambda is, the more degenerate the singularities are, and also it's a direct direct generalization to the real case of the log-canonical threshold in the complex case. Let me just spell out the relationship between the two. So if let's say FC is an holomorphic function on a complex manifold, then there is this quantity called the log-canonical threshold of x, which is defined basically in the same way, except that you put a 2 here because complex manifolds are because C is dimension 2 over R. And so the log-canonical threshold of FC turns out to be the same thing as you take FC, you take its absolute value and you square. So now that's a real analytic function on the underlying manifold. Then you take lambda of this, and you so this real log-canonical threshold is in the sense a generalization of the complex one. And we will see that in some ways it's very similar, and in others it's quite different. So the way that I've set the definition, it's not clear that these things are finite. Right? In general, they are not. Let me just spell out it's a lemma. Right? That first of all, so lambda f is finite exactly when P of f is non-empty, and lambda x is finite exactly when x is in P of f. And in that case, so this the function which to an x associates this local real log-canonical threshold. This is upper semi-continuous. So it can drop when you specialize. And something which, okay, I'm sort of spoiling the fun here, but something which is not at all clear from and of course, if you've seen the complex story, you know this, that this invariant is actually a rational number. I'll explain why. And so in particular, it's basically locally constant, except when it drops. And we'll see well. So there's a stratification and so on each stratum it is constant. And finally, what's the relationship between the global one and the global real log-canonical threshold is the minimum or the inf. This is kind of why I don't know. So inf for agent for any analytic function and minimum for any reasonably behaved analytic function, for instance, for polynomial. And so in particular, you can basically always reduce to the local picture. Okay, so so as it turns out that it's as its complex cousin, it is actually very difficult to compute in practice. Probably even more difficult than in the complex case. But there are some simple cases where. So some simple formulas that you can do. So let's say that we have two such functions. So first of all, I mean, generalizing the first example, right? Lambda of f to the n is 1 over f lambda of f. Again, and again, you know these formulas, you should sort of imagine that there is a local and a global functions. Lambda of and let's say that so this is on one manifold and G is on another manifold. Look at the product situation, and so in that, for instance, the log-canonical threshold of the product of this function on the product, the product on the product. This is just the minimum of the two. And if f and g are non-negative, then the real log-canonical threshold of the Thom-Sebastiani sum of f and g. So just this is a fancy name for just this, the sum of the product. This is the sum of. This is maybe the first place if you're familiar with the complex story where you maybe feel that things are getting a bit different. So first of all, in the complex story, there is a kind of similar formula, but of course there's no positivity or negativity. But in the complex case, maybe let me actually call this lambda c, right? So let me just write the complex formula for emphasis. So this is the minimum of 1 and the lambda c of f plus lambda c. And so I'm going to be more precise about this, but one of the main differences between the complex and the real story is that the complex log-canonical threshold is always bounded, is always between 0 and 1, whereas the real one is can go this. We'll see how far it can go. That's one of the main differences, and also the role of positivity. Sure, let's see. Where's the eraser?
They're on the right hand side.
So any questions so far? So using these formulas, you can compute a few examples. So mostly when in situation where you can sort of separate the variables and use disjoint set of variables and build the function this way. Okay, let's look at some examples. So I didn't say anything about the proof, but so actually the last point that I mentioned, the one about the Thom-Sebastiani sum, is not so clear from this definition, and that there will be an equivalent analytic characterization which makes this obvious. So one basic example, and of course it's important because of resolution of singularity, and monomials are important, is the case of monomial. So first of all, the log-canonical threshold of a monomial is always sort of attained at 0. And it's just the minimum of the 1 over Ni, as follows by the previous result. And just let's do a picture for x squared y4. So this is the 0 locus, and on this line, the real log-canonical threshold is equal to 1/4, and on this line minus the origin, this is 1. So you see that along this thing, the natural stratification is this, and the complement of the origin in this line, and along this it drops when it comes to the origin. And this is really the typical picture. So we can also do sums, but because we have this constraint on the positivity, we can only do well, at least we can only do easily this kind of sum, and this is 1 over 2ni plus it's the sum of the reciprocal of the exponents. And so in particular, we recover if you take a quadratic form, and not even necessarily full rank, you see that you get this r over 2, and so for r equal d, you get d over 2, as in the introduction. Let's see. I will try to sort of focus on the features the features that are special to the real case, right? That's maybe the more interesting thing. So I mean, if you have a real analytic function and a point and a 0, there are two possibilities. Either the function changes sign around x, or it has constant sign, and those are quite dramatically different in real geometry. So if f changes sign at x, this is equivalent to saying that Vf has a smooth R points, let's say near x. So x is not necessarily a smooth point, but actually the smooth R point will be dense in the neighborhood. And so this actually implies that the codimension of the 0 locus is 1. Let's say if f is not 0. So that's sort of the case that we're used to in algebraic geometry. It's the Hauptstellen that codimension of an hypersurface is 1. But then the other case, which is the case of interest in real geometry, is that when f is of constant sign, and then I should say also that because there are smooth points, and that smooth points have a log-canonical threshold equal to 1, as is easy to see. Then that implies that the log-canonical threshold at x is less or equal to 1. So again, this is similar to the real story. But if the f has constant sign, then the best thing you can say in general is that this real log-canonical threshold is less than the codimension of the 0 locus divided by 2. So I should say f not 0, but not identically 0. Otherwise, there are some silly pathologies that I want to avoid. So in particular, it's always less than d over 2. And in fact, this let me write it actually. So when is this attained? This is actually equivalent basically by Morse lemma to the quadratic case. So in some local coordinate, f is so-called. Okay, so yeah, we've already seen some of the sort of contrast with the complex case. So in particular, the fact that it's bounded by 1 in the complex case. And let me just give another example, which maybe makes this point clear. So if you take lambda of this, so we saw what this is. This is 3 over 2. And on the other hand, I can look at lambda of x squared plus y squared minus z squared. So this turns out, this, although you can't actually prove it from what I've said so far, this turns to be 1. So these two are different. But actually, this is the complex log-canonical threshold of x plus y squared plus or minus this. Because over C the sign does see the sign. And there are lots of ways in which there are lots of ways in which the behavior of the real log-canonical threshold is more subtle. So behavior subtle. So I'm going to list a few, but probably not. I mean, so in one of the most sort of beautiful property of the complex log-canonical threshold is the fact that if you have a family of function, then that is also a semi-continuous. I mean, under some assumption, some pure assumption, but this is also due to the Bayesian polar. This is not true. Another property which unfortunately does not hold if you have a smooth hypersurface, then the complex log-canonical threshold of the restriction turns out to be always less or equal to the complex log-canonical threshold of F. So this is sometimes called inversion of adjunction, or it's sort of part of the circle of ideas in birational geometry. But this is not, again, not true over R. Yeah, let me just write a counterexample. I think I need 4 variables, but yeah. I think this is okay. And H is the hypersurface double. So another important property of the complex log-canonical threshold is that so minus the complex log-canonical threshold is always the largest root. So this is more for people who are sort of familiar with the complex story. Then I will sort of come back to more elementary consideration. The largest root of the Gelfand-Leray polynomial. But on the other hand, minus the log-canonical threshold of F is one root of the Gelfand-Leray polynomial. It still makes sense over R, but actually it turns out to be the same over R and over C. So it's kind of an algebraic. So it's in general, it's another root, and yeah, it's not clear. So this cycle. It's follows from there. I mean, in the complex case, also proving that it's one root is not difficult. There are difficult parts of the root that is the largest root. And the argument that it's one root also basically works in the real case. Okay, so then I want to talk briefly about resolution of singularities and how you, and one way that you can try to compute. And again, if you're familiar with the complex story, you want, I mean, there's basically the complex story with one little twist, which I will point out. So first of all, you need of course, you need the real analytic version of the Hironaka theorem, but that was basically already due to Hironaka. So it's log resolutions in real analytic. Okay. And I will state it relatively, yeah, somewhat imprecise way. So there is a real analytic modification, which basically is obtained by a sequence of smooth blow-up, but in the analytic case, you have to be a bit careful about compactness issues and so on. But so in particular, this means that this is proper and birational. Such that so locally on X tilde, so there exists a local coordinate. I'm going to express it in the most analytic way possible. I'm not going to talk about divisors or anything like that. Just about making a function monomial. There is local coordinate, let's say U1, UD. So that first of all, the f composed with pi, so f of pi of u, so is equal. And again, this only also somehow locally in some charts of X tilde is some function which is a unit, like a non-vanishing function, real-analytic function, times a product of ui ai. AI is some integers, and also the determinant of the Jacobian matrix, which again because you have chosen some local coordinate, this you need to choose local coordinate upstairs and downstairs, but doing this implicitly. So this Jacobian determinant is also basically the same case. This is the unit times the product of ui gas. Okay.
So it's what's called local monomialization, right? And
yeah. So this form only holds. So the idea is, upstairs there's a normal crossing divisor, and depending on which intersection of branches you're at, you will have more of these coming up.
And is it related to those real-oriented blow-ups like you have?
No, this is purely there's no.
I see.
No, this is really the complete parallel to the algebraic resolution. Okay. And so now a theorem which basically goes back to what we are. I think is the following thing. So first of all, it's a formula for lambda of f. So lambda of f is going to be a minimum over charts, and again, this minimum should be an inf, and a minimum over I, where these I are sort of depend on these indexing of the local coordinate depends on the choices and so on. So this is not somehow the most sort of canonical way to express it. It's maybe the simplest one to digest. So it's the minimum of this ki plus 1 over ai. And same thing for the local one is the same minimum over charts, and then you take the minimum over those I such that the point x lies in the image under pi of the vanishing losses of ui. So this is really not difficult. This is just an application of the change of variable formula, and you put in the change of variable formula. You plug in this thing, then you apply Fubini, and basically you reduce to the monomial case. But a sort of deeper thing, which follows from the same argument, but it's kind of very important for the rest, is that there is an Archimedean zeta function in the story. So the Archimedean zeta function, or maybe it's better to call it the Archimedean zeta distribution, and that's really how Atiyah was thinking about it in this paper. is the correct thing. So it's, and I will write it as a distribution just to. So if you take some compactly supported function on x, and then you can form this zeta function, let's say at s, and apply to phi. And what is it by definition is the integral of f to the s phi, and then I fix the global volume form on x. Just if x is not integrable, then you have to just work globally. So this, I mean, by construction, essentially, this is holomorphic in S. It's with real part of S greater or equal to 0, and the point is that this extends to a meromorphic family of distribution. Meromorphic in S. So this is called also the Archimedean zeta function, and the Archimedean Iguza zeta function, because Iguza contributed a lot to this story. And so what's the relationship with the previous thing? Well, the poles of these meromorphic things are distribution are real and negative. And lambda, let me state it for the local thing. Lambda of x, for instance, is minus the largest pole of just integral. You apply this. You integrate this. You do this thing over a small enough neighborhood. So again, if you've seen this the complex invariant before, you might be a bit confused here, because this looks exactly like the complex formula. But the difference is that if you start, let's say we started with a real polynomial, and we apply just resolution of singularities over algebraic resolution of singularity over R, then we would get exactly the same picture, except that these choices of local coordinates might not be, you might not be able to choose them over R. Or in other words, the exceptional divisors of the resolution as a scheme may not have real points. And that's exactly what accounts for the difference between the real and the complex invariant. Let's see. Yeah, I wanted to do an example. Maybe I'll leave it as an exercise to see this difference between the real and complex case. I would suggest you look again at the quadratic form in free variable. Look why the log-canonical. Why is it that lambda q is real and is different from C one using this right? Okay. Okay, so another striking corollary, which I mean, as far as I know, there's maybe in the complex case there are other ways to see this. But for instance, in the real case, I don't know any other way to show that that these are rational numbers. This is kind of surprising. I mean, this is certainly, if you take the definition that I gave at the beginning about integrability of powers, it makes sense for basically any function, and it's certainly not true that there's this threshold is rational for anything. So this is kind of really a property of analytic functions. Another corollary, which maybe is not so clear, but is the fact that actually this only depends on the Taylor expansion of F. So if you're on the class in the completed local ring, which is power series ring in dividable. And the reason is that actually resolution of singularities as as Hironaka showed, it's a really flexible. I mean, the Hironaka's framework and the sort of improvement that came after him. It's a very flexible framework. In particular, you can also work with things over like formal schemes or and things over power series ring. And basically, if you take I mean, that's maybe a bit of a big hammer, but you can compare some other. You can take one of these resolutions, then sort of formalize it, complete it around this point, and you get a resolution which also compute the same thing. So if you have to, I think you see what I mean. And in fact, you can, using this thing, you can even extend this real log-canonical threshold to power series themselves. In the complex case, this has been studied a bit. I don't think anything has come in the real case. Like not necessarily convergent powers. Okay, so I promised you some more analytic characterization, but it turns out that to prove them, you actually have to use this Archimedean zeta function. At least that's the only proof I know. And this is, yeah, it's quite a long story, but yeah, it can be sort of summarized in one small diagram. So let's try to do that. So you have this. You have this Archimedean zeta function.
Should break it.
I just used a small one. So we have this Archimedean zeta function or distribution. So then you take an inverse mailing transform of this function, or again distribution, and you get basically what's called various as a part of singularity, maybe the Gelfand-Leray form. Yeah, just I'm not going to explain exactly what I mean by this, but then once you have this thing, then you can just integrate, and you get the volume of sublevel sets, and I will explain what. You can take the Laplace transform, and you get this Laplace integral, or you can take the Fourier transform, and you get oscillatory integral. One particular type of oscillatory integral. So, and actually, a lot of the theory has been sort of developed to understand this case, but in some sense, I'm actually much more interested in this one, and I'll try to say over why. Okay, so one property of this inverse mailing transform is that if you have a meromorphic function with a nice enough pole structure, then you get, by inverse mailing transform, you get some asymptotic expansions. So asymptotic expansion in let's say t to the a minus log t to the b, and I will say a word about this. And then when you apply this, you get again asymptotic expansions. So let's just state something more precise. And so this appears. So this does not appear in Attia's paper, but so it's developed in the book. I mean, I think the ideas are probably due to Rashenko originally, but so it develops in this book of
without this. It's Rashenko.
Ah, something. Okay, so yeah, let me try not to be too precise. But so I take a point, I take a small enough neighborhood of this point. So at this point, it's kind of important to introduce a secondary invariant, or rather, let me define mu f of x. So this is the multiplicity of minus as the pole of the zeta function. So yeah, you should probably not call it the multiplicity, maybe the real log-canonical multiplicity. And then what happens is that you have asymptotic. So I'm not going to write the full asymptotic expansion. I'm just going to write the first term, which is already interesting. So if you take the integral, so if you take the volume of a sublevel set of absolute value, you get that this is a constant, which we don't know much about, times t to the, so as t goes to 0, t to the lambda x minus log t to the mu x minus t. And then the exponential integral version. This is again intersective. So this is n to the minus lambda x log n. And for instance, as an exercise, you can use this to show this Tom Sebastiani property that I. Okay, so I want to get to the jet scheme, so I'm almost there. So let me just mention my main motivation for getting into this subject. It actually comes from statistics. There is this thing called singular learning theory. And it's basically it's sort of the mathematical theory of like Bayesian statistics or Bayesian statistical learning theories for so-called singular statistical theory. And the sort of important point is that this is actually most models, in particular in modern machine learning, now this slide. Awesome. So this has been developed by the Japanese statistician Gelfand-Leray. And the basic idea is that there's a lot of notation, a lot of context, and it's kind of difficult to summarize. But so, roughly speaking, in Bayesian inference, you have this Bayesian sphere distribution. On the set of parameters of your model. So let me call this parameters of the model, and in this application, then basically always in machine learning, or it's some nice subset of RD. So the idea is that this posterior distribution concentrates as the number of data points, so n, which is the data points. So sample from the true underlying distribution. So concentrate around the set W0, which is the minima of a certain function. The minima of a certain function k, which is the kind of relative entropy function. And for typically, this is a real analytic function because these statistical models are built from very simple analytic functions. And this and the idea is that the point, I mean the link between the fact this concentration is controlled by the singularities of K. So this is always a negative function. It's controlled by the singularity of K, and in particular, and the most important the contribution of this to this concentration is lambda. And so this theory so it was developed by Watanabe in this sort of context of theoretical Bayesian statistics, but recently it had some very very beautiful and interesting and sort of active applications to the interpretability of neural networks. So trying to understand how neural networks compute how they learn. And so this has been developed in particular by Dan Murphy and plus many collaborators. Yeah, now let's get to GenFP on the last 8 minutes of the talk. So I've already basically given the definition, but so in general, right now, my X is now a real analytic manifold. So again, this I think of this as Taylor expansion to order M of germs of curves, germs of analytic or infinity, it doesn't matter, but it's best to say analytic terms on X. And so locally on X, this is again X times RD to the M, where these record all these Taylor coefficients. In particular, J1 of X, this is just the tangent bundle of X. Sorry. And so inside of this big real analytic manifold, there is the jet schemes of F, which again are as introduction. It was basically germs of curves such that when you plug them into F, you get which vanishes up to orders M. So these things form a nice tower of real analytic sets, right? Because you can always truncate more. So J0 of F, this is just the vanishing locus of F inside of X. This is the kernel of DF. So as inside of the sort of for over every so this lives inside the tangent bundle, and so it's the sort of putting together all the kernels of all the differential at various points. Of this notation, I mean, it's a bit of an abuse, but it's okay. And so now here's the connection between the two parts. So this is in the complex analytic case. This is a theorem of Mustață, and of course I apologize for the absence. Okay, I learned this at some point, but so this is for the complex in algebraic geometry. So I extended this to the real analytic case. So here's the formula. So this generalizes the observation that I did in the introduction just for quadratic forms. And yeah, so you take the codimension of this theorem of F inside, so this codimension inside of so ambient big manifold. And we take the minimum. And this is really a honest minimum. Well, so again, there's, but it's really it's an honest minimum. It's said that it will be attained, and in fact, it will be attained infinitely many times. So in fact, there exists again maybe so locally on X. So the mean is the same for all M sort of in there, and you take an arithmetic for the arithmetic progression M minus 1. So you want these, the GM plus 1 should be in an arithmetic progression. So in other words, sort of more degenerate singularities have larger jet schemes. So I'll just say a word about the proof. So it's so the original proof of Mustață uses motivic integration and the Hodge sort of the Hodge zeta function. This I think this strategy can be adapted in some cases using, because there are people who have worked on real motivic integration, so Pauzinski, Fichu, Campesato, and others, and using in particular this Fichu zeta function. I think you can prove this for like Nash functions, but for general real analytic function, I don't see how to do it. But fortunately, there is an alternative formula which has somehow has the same roots, but same geometric roots, but gets around motivic integration explicitly, which is due to Ein-Lazarsfeld-Mustață. And the idea is to study the geometry of you need to study something more general than jet scheme. You need to study the geometry of all contact loci, which are very similar to the previous thing, but it's a stratification of X by the order of vanishing of S longs. And the main tools to do this are things like you need to work actually with arcs, with the associated arc scheme as well. But you need some kind of arc lifting property, and you also need what's called like Kontsevich lemma or the Denef-Lozer lemma. But in the real, so you need the real analytic. It's actually a real sub-analytic, and you kind of need to go into the Kontsevich lemma, which fortunately for me was worked out eventually by Koike and Pauzinski. And you apply this tool to a resolution of singularity. So in the same way that you would compute a motivic integral, but motivic integral does not appear explicitly.
Remind what Kontsevich lemma is? Can you remind what Kontsevich lemma is?
It's a little bit technical, but it's basically what if you have a resolution or a real modification, you have an induced map on jet schemes. And it's telling you which it's giving you some vibration structure on the map on some contact loci,
like GM or A1.
But again on some contact loci. Okay, so let's see. So I have to conclude. So first of all, this is clearly something that experts in the subject could could have found, but as far as I can tell, it's not been done before. But it's clearly uses the ideas that were already in the literature. So in the so yeah, what's the interest of this kind of result? So in birational geometry, in complex birational geometry, this kind of arc theoretic or jet theoretic approaches have been used to study the log-canonical threshold and other sort of discrepancies, type invariants in complex birational geometry. For me, so I mean, one reason that this is quite nice is that this is an the jet schemes are an intrinsic geometric object, whereas the resolution is a non-canonical object. And yeah, I'm sort of trying to understand if there is a relationship with the statistical story, which I mean, so I should have said the statistical story sort of comes out of the Laplace rule. In Bayesian statistics, you have to compute this kind of integral. Yeah, and so I've been looking at trying to connect directly the geometry of the jet schemes and these basically the Gelfand-Leray, the asymptotic of the Gelfand-Leray form, but so far I don't have something to report. Yeah, and maybe one last remark about this, which is that, so I said that there are some subtlety. I mean, this lambda has some subtleties, and I think that this formula has some chance of eliminating a bit these subtleties. Well, one reason, for instance, is that if you have two non-negative functions, then it's easy to see, and it's that the jet scheme of f plus g is just the intersection of the jet schemes of f and the jet scheme of g. Or similarly, so if you're the jet scheme of f restricted to h, right, is the jet scheme of f intersected with this jet scheme of h inside of the jet scheme of. So there are pathologies with about the behavior of the real log-canonical threshold, but this gives you some geometric ways to try to understand when they hold, when they fail. Let me stop.
Thank you.
Are there any questions for Simon? So maybe can you so again for this relationship with the statistics part, you just mentioned that this formula somehow appears in the kind of in the statistics world, and then on the other hand it's related to the log-canonical threshold of the function.
Yeah, so this is really going from this to the Watanabe's result is I mean, it involves quite a bit more work, but basically in Bayesian statistics you have to compute integral like this, but where this is actually this is not this k. This is something which depends on the data. Where this k is sort of this function k is basically an expectation of kn over all possible data sets. It's what's called the population loss function, or the so you have basically integrals of this kind, where this is the prior distribution. So this is basically what the Bayesian let's say the Bayesian posterior looks like this, but then you have to divide by, you have to normalize it into a probability distribution. And basically the idea of Watanabe, which is that this kind of this function kn sort of fluctuates. It's really a random function which depends on the data and sort of fluctuates around its average k. And you have to, and basically this integral turns out to be controlled by the behavior of k under some assumption, and then so then you can apply basically these results and get the
So usually when like my definition that I usually work with something like log-canonical threshold is it has something to do with the canonical line bundle, like top which powers of differentials. Is there any sort of way of seeing this in the real case?
probably, but I really wanted to use the minimal amount of actual like analytic geometry. I didn't want to use sheaves in the analytic geometry since all these quantities are local anyway. And unlike in I guess in complex geometry, a lot of the interest of the topic is also the global situation and with like smooth projective varieties and so on. In the real case, the global situation is much more wild, and so yeah, the thing that you can understand really is more the local. And then locally, you don't need any sheaf theory to, and just trivialize. I mean, at some point I said I choose a global volume form. I just trivialized the topic zero power of Gamma. So it turns out it doesn't matter. It just changes these. I mean, it changes the integral, but it doesn't change the asymptotic.
Maybe it's very related to my question. So are you, maybe I'm just kind of confused about that. So are you working with the real analytic case or just real?
Yeah, real analytic.
Real, and it's somehow the global geometry is still very wild. So
yeah, it can be.
more questions for someone? Yeah.
I need to take the bus number 2.
Yes.
Let me stop there.
You're not doing like the